Usually people associate computation with computer science and mathematics. Well, in this presentation, I'm going to demonstrate how computation is actually a universal human experience, and we can find expressions of it across all the fields of human knowledge. We can find it in all of the world religions, we can find it in mythology, we can find it in philosophy, the natural sciences, and the social sciences, and beyond. So, for those of you who are new to the series, this series is about the architectonic of simulation. The architectonic of simulation is a model that accounts for, describes, and puts into taxonomic arrangement all simulacra or all kinds of experiences across all simulations or all representations of reality. Now, the first video was about the architectonic of simulation in the context of an overview. And then I've started a series that will go into each of the brackets of the taxonomy to give a more detailed explanation about what they are and the different kinds of expressions that we find across all of human experience. And the previous video was on the universal prototype, and so this video continues with computational simulacra. This presentation is divided into three parts. Part 1 is on the definition of computational simulacra. Part 2 is on expressions of computational simulacra. And then Part 3 will be a discussion about computational simulacra. Part 1, definition of computational simulacra. So this part divides into 4 sections. The first section will be defining computational simulacra, and then that will be followed by the computational domain, computational modes, and then computational tessellations. And each one I'll give definitions about what these are, and then I'll also present some propositions about their characteristics. Defining computational simulacra. So etymologically, the term comes from the Latin cum, together, and putere, to think and reckon. And there's a lot of definitions that people give to computation. I'll give 2 definitions. I'll give a simple definition and a complicated definition. The simple definition is just a system that performs actions on itself. And the complicated definition is a self-referential system that orients, transforms, and iterates encapsulated complex patterns. As we go through the definitions and the proposed properties of computational domain, computational modes, and computational tessellation, you'll see these words come up, and so you'll then understand why I use these words in the complicated definition of computational simulacra. Computation and context. So first, there is computation fitting into a larger whole, and then second, there's how computation divides into parts. So how computation fits into the larger whole in the architectonic of simulation is that there are 3 orders of simulacra in the architectonic of simulation. The first order is computation, the second order is ratiocination, and the third order is instantiation. And so how this works is that computation is the universal system that performs actions on itself, and then the second order is the ratiocinators, and these ratiocinators are the means in which computation computes. And then the third order, instantiation, are the instances that occur through the ratiocinations. Now, in terms of computation dividing into parts, computation consists of a single domain, 3 modes, and 3 tessellations. The computational domain is recursion. The modes are static, dynamic, and multidynamic. And then the computational tessellations are objectivity, subjectivity, and transjectivity. And so what we're going to do in this first part is we're going to go through each of these and give definitions of them and then some proposals of what their properties are. The computation domain. So in the order of computational simulacra, there's only one domain, and that domain is recursion. The etymology of recursion is from the Latin recursio, which meant returning back. And I think that is pretty good in terms of like a simple definition to give to recursion. The definition that I present here is more of a complicated one. The definition that I give to recursion is the self-referential character of an architecture, process, or and their calculation. And the reason that I give this definition is because in the three orders of simulacra, the first order being computation, the second order is ratiocination, and ratiocination is the means in which computation computes. And so the self-referential characteristics of the computational domain of recursion recur again and again and again in every conceivable way in all of the architectural, processual, and calculatory ratiocinators and their instantiations. So in terms of the ratiocinators that are architectural, which are space, time, energy, form, matter, apparatus, psyche, semiotics, and schema, these are all going to exhibit recursive characteristics. And in terms of the processual ratiocinators of automation, transduction, concretion, abstraction, principle, paradigm, panoptic, phasic, and deicic, these are also going to exhibit recursive characteristics. And then the architectural and processual ratiocinators combined together into different kinds of calculations are going to be calculating recursively the characteristics of the computational domain. So I have four propositions for the computational domain. The first proposition is that the computational domain is self-generative, and this means that computational systems generate their own simulacra. The second proposition is that the computational domain is self-returning, and this means that computational systems return simulacra that they create back on themselves. The third proposition is that the computational domain is self-referential, and this means that a computational system can only reference itself by means of the simulacra that it returns. And the fourth proposition is that the computational domain is self-arranging, and this means that a computational system's return simulacra is arranged in accordance to the pre-existing arrangement of the simulacra within its system. Computation modes. So in the computational order of simulacra, deriving from the recursive domain are three modes. The modes are static, dynamic, and multidynamic. Static is etymologically derived from the Greek word statikos, which meant to cause to stand, skilled in weighing. And in the 19th century, it took on the meaning of having to do with bodies at rest or with forces that balance each other. So the definition that I give to static simulacra is simulacra of equilibrium between interaction. And synonyms would be things like rest, entity, state, type, structure, and architecture. Dynamic simulacra, the word dynamic is etymologically derived from the Greek dynamikos, which meant powerful, and then in the 19th century it took on the meaning of active, potent, effective, and energetic. So the definition that I give to dynamic simulacra is simulacra of interaction between equilibriums. And synonyms would be things like disequilibrium, motion, action, event, operation, relation, and process. Now, multidynamic simulacra is a word that I coined. Etymologically, it combines multi, which means many, and ICOs in the manner of the definition that I give to multidynamic simulacra is simulacra of simultaneity between multiple interactions of equilibriums, a hypernym for static and dynamic. And so synonyms would be things like equilibration, rest in motion, entity action, circumstance, function, system, and calculation. And I think it's important to clarify that there's a difference between equilibrium and equilibration. By equilibrium, I mean to say a equilibrium that has been previously established between interactions. And by equilibration, I mean equilibration as the coming into being or the creation of a new kind of equilibrium from the interactions between the interactions. So there are three propositions that I have for computational modes. The first proposition is that computational modes are orientational. They are circumstances of simulacra. So static is the satisfiability, the dynamic is the junctive, and the multidynamic is the collative. And proposition 2 is that computational modes are transitional. They are changes in simulacra from one state to another, and they run in two directions. They run forward and they run backwards. So when computational modes run forward, it's assembly, it's the synthesis, it's combination, and it's unification. And when computational modes transition backwards, it is the disassembly, it's the analysis, it's separation, it's division. And then the third proposition is that computational modes are iterative. And this means that they repeat on themselves to create tessellative patterns. Computation tessellation. So there are three tessellations in the order of computational simulacra. Recursive modes iterate into three kinds of tessellates: objectivity, subjectivity, and transjectivity. Computational objectivity therefore consists of object static, object dynamic, and object multidynamic. The object static is corporeal entity simulacra, and these divide into ratiocinator architectural domains of form, matter, and apparatus. Object dynamic are tangible action simulacra, and they divide into ratiocinator process domains of automation, transduction, and concretion. And object multidynamic is the simultaneity of corporeal entity simulacra with tangible action simulacra, and they divide into ratiocinator calculatory domains, which are the simultaneity of object static with object dynamic, and they can be any of the ratiocinator architectural domains with the ratiocinator process domains. Computational subjectivity. Computational subjectivity also has static, dynamic, and multidynamic modes. The subject static are psychurial entity simulacra, and they divide into the ratiocinator architectural domains of psyche, semiotic, and schema. Subject dynamic is the quasi-tangible action simulacra, and they divide into ratiocinator processual domains of abstraction, principiation, and paradigmatization. And the subject multidynamic is the simultaneity of psychoreal entity simulacra with quasi-tangible action simulacra, and then this divides into ratiocinator calculatory domains, which are the simultaneity of psychoreal entity and quasi-tangible actions. And then finally, we have the computational transjectivity. And transject static are ethereal entity simulacra, and they divide into ratiocinator architectural domains of space, time, and energy. Transject dynamic are intangible action simulacra, and they divide into the ratiocinator architectural domains of panoptic, phasic, and deicic. And then, of course, the transject multidynamic are the simultaneity of ethereal entity simulacra with intangible action simulacra, and their ratiocinator calculatory domains are any ethereal entity with intangible action. So there are only two propositions that I'll make here about tessellation. The first proposition is that computational tessellations are encapsulative. They exhibit nesting, which creates the property of inside and outside. The second proposition is that computational tessellations are complex. They exhibit horizontal, vertical, and diagonal complexity. Horizontal complexity is simulacra of the same rank. Vertical complexity is the simulacra of ascending and descending ranks, and diagonal complexity are returns to ranks. So, computationally, anything can relate to anything else through these different kinds of complexity. And all the kinds of things that we talk about, like hierarchy and heterarchy and panarchy and anarchy, can all be attributed to these computational tessellation complexity characteristics. So there's one more thing that I'd like to add that has to do with the relationship between encapsulation and diagonal complexity. Object simulacra tend to be associated with externality and subjective simulacra with internality, and transject simulacra with pervasiveness throughout object and subject simulacra. But any simulacra can be returned in any combination outside the boundaries of these taxonomic classifications as a function of the computational domain of recursion, because all simulacra are descendants and inherit the characteristics of their parent simulacra. So, for example, objects can be contained within subjects, subjects can be contained within objects, and transjects can be contained within either. So while we can have a very orderly, clear taxonomic division of simulacra deriving from higher classes of simulacra, any of the sub-taxonomic classes that are derivative of the computational tessellations, and I'm talking about the ratiocinators, any of the ratiocinators can relate to any of the other ratiocinators. So you can have ratiocinators that are derivative of objectivity corresponding with ratiocinators of subjectivity or transjectivity, and then any combination between objectivity, subjectivity, and transjectivity in that respect. In other words, you can have any architectural ratiocinator correspond with any processual ratiocinator to combine together into any kind of multinamic ratiocination. And this is because of the diagonal complexity, where anything can return on anything else. So even though in the taxonomic concept we can sort of have an idea about the encapsulation of internality and externality, in actual life and experience, what is internal and what is external is circumstantial to the position in which you are making sense of the world. So what seems like is external to you in a larger scope is internal to something else. So internal and external are relative in many regards, such that there's a sort of absolute idea about the encapsulation, but it's also relative to circumstance. Part 2, expressions of computation simulacra. So what I'm going to do here is I'm going to talk about computational simulacra as it is expressed across a wide range of different conventional categories of human knowledge and experience. I'm going to start with religion and mythology, and then move on to philosophy, physical sciences, psychology and behaviorism, computer science, and then finally on the propositional calculus. Religion and mythology. So I'm going to divide this into theisms, deities and demigods, rebirth, and cosmogony. The first topic is theisms. So there's theism and there's atheism, but in both cases there's some variation of an expression about aseity, which is the idea that things are self-created. So theists generally hold the idea that there's this God that created everything, and that God also created itself. And in atheism, which is people not believing in the existence of God, there's still this belief that reality somehow created itself or it always existed. But in any of these cases, there's always going to be this characteristic in the conception of the representation or the internal simulation of reality that reality created itself or it's creating itself recursively. Now, we can talk about monotheistic religions of God making itself, and we can find expressions of this in Judaism, Christianity, Islam, Sikhism, Rastafarianism, and Zoroastrianism. We also find expressions of this in polytheism, where gods are the gods of their own domains. So in a lot of these, there are still concepts of reality creating itself or some sort of God of everything creating itself and then from itself creating everything else. And we find expressions of both of these sorts of things, of gods creating everything and gods being the gods of their own domain in Hinduism, in Shintoism, Greek and Roman myth, in the Aztecs, in the Celtic myths, and in paganism. Now, we also have pantheism, which is the idea of God dividing itself into the universe. And we find this for example, in the Hindi Purusha and in the Chinese Panu. And then there's also another kind of theism, which is panentheism, which is that God pervades the universe but is not part of it. And we'll find different variations of this across both monotheistic and polytheistic worldviews and universe views. Now, in terms of deities and demigods, there's pantheonic deities that are expressions of characteristics of the modes. So in Hinduism, there's the Trimurti, which has Vishnu, Shiva, and Brahma. And Vishnu is generally characterized as this preserver deity, Shiva is the transformer, and Brahma as the creator. And these gods are personifications of static, dynamic, and multidynamic. Vishnu as the preserver, as the static, Shiva as the transformer, as the dynamic, and Brahma as the creator or the multidynamic, bringing about new kinds of equilibriums into the universe. We also find other parallels to the computational modes in the Chinese Taiji Tu, with yin being the passive and yang being the active, whereas yin is associative with static and yang it can be associated with the dynamic. And we also find another common characteristic of the modes in the Roman Janus, which was the god of passages and transitions through conflict. And one of the characteristics that I propose for the modes is that they're transformational. They go through static, dynamic, and multidynamic modes, and then this repeats, it recurses. And so Janus is an expression of that. But then we have other things such as the demigods, which are tricksters that show people blind spots, and they cause the transitions from one state of things into another. So some examples of this are the African Ekwensu and Anansi, the Indian Hanuman, the Inuit Amaguk, the Maori Maui, and the Norse Loki. And we also find demigods that fulfill similar kinds of functionalities, bringing about transformations or great movers of change as heroes. And so we have characters like the Jewish Abraham, the Christian Jesus, the Chinese Buddha, the Hindu Krishna, and the Greek Odysseus. When it comes to rebirth, the association with recursivity is fairly obvious. In Christianity, there's the concept of baptism and resurrection, which is clearly transitioning from an old way into a new way. It's recursing into something fresh. And in terms of the resurrection concept, it's about an old way of being dying and then being reborn into something new. In Buddhism, there is the dukkha, the samskara, and the nirvana concepts. And the dukkha has to do with the unsatisfactory of life or a certain state or a way of being. And samskara is about the impermanence of everything, and nirvana, the free from rebirth concept. And the thing about these is that they do correspond with the modes of computation, because you have like a certain way that things are, a certain static, and then you have the impermanence, which is that dynamic, that is the change of everything, and then you have the nirvana, which is wanting to be free from the rebirth cycle, which is finding some sort of like universal state, or a universal characteristic of being that can persist across all of the rebirths or changes. And whether you take that as literal or symbolic, in both ways it makes sense. And then in Hinduism, there's transmigration from karma. So the recursivity is expressed here in terms of things that happened previously in a previous way of life or a previous state of being, carrying over into a new state of being and having an effect on what that is. And in Greek mythology, there's the symbol of the phoenix, which is death and rising from the ashes. And so, again, you can see an expression of the recursivity of one way of being dying and being replaced by something new, a new version of the entity. And then there's the universal symbol of the Ouroboros, which is a symbol that has appeared all over the world independently between cultures that had no idea about each other. And the Ouroboros is a snake that eats its tail, and the tail biting is a reference to everything consuming itself, everything going in a circle, everything recursing back on itself, leading to higher degrees of complexity of integration. And then last to be mentioned is cosmogony. So cosmogony is the realm of knowledge concerned with different ideas people have about how the universe came into being. And so some of the examples here are the cosmic egg, order from chaos, cyclical time, and the world tree. So with the cosmic egg, the general concept with the cosmic egg is that there was some sort of unity of some kind that got divided into everything. And we find examples of this in the Greeks with the Orphic tradition of the hermaphroditic Phanes and Protogonos. And we also see this in the Chinese Pangu, hatching from the egg and dividing into everything in the world, which we had mentioned earlier before. And then the Finnish Kalevala. And in terms of order from chaos, there's the Hebrew out of darkness came light, the Siberian water and fire, the Babylonian Esuma Elish. And in terms of cyclical time, we have the Jainists Kalachakra, or the cycle of the universe, where there is an idea that everything that exists will sometime come to an end, and then the universe will be reborn, and it happens again and again, over and over again. And the Mayans having their repeating cycles of creation and destruction as well. And then the Egyptian Ra fighting Apep every day as the sun sets into the darkness and then rises again. And then, of course, we have the world tree, and this is another universal symbol that's all over the place. So some examples would be in the Jewish, Christian, and Islamic concept of the tree of knowledge, the Vedic Kalpa Vriksha, and the Norse Yggdrasil. So with the cosmic egg, we can see an expression of the computational modes running backwards, dividing into everything that exists. And in terms of order from chaos, we can see the modes running forwards, which is that things are assembling into greater wholes. And in terms of cyclical time, we can see expressions of recursivity of everything. And in terms of the world tree, we have the symbol of everything being bound together on a single trunk, and then having branches that divide into further branches that divide into further branches, as the overall sort of unification of all of the differences that exist in all the divisions of all the things, still being unified by that trunk. Physical sciences. So I'm going to just talk a little bit about some examples from physics, biology, neurology, and then just generally across the physical sciences. In terms of physics, we can first start out with Newton, and he had the concepts of rest and motion, and he produced all these principles that were based on it that we still use today. Well, it's pretty obvious that rest and motion are expressions of static dynamic in matter. And matter is one of the universal ratiocinators that I'll talk about in the future video. Then there's Petronero and Guth. Petronero and Guth both talk about the fractal nature of the universe. Petronero talks about the fractal distribution of galaxies from a mathematical context, and then Guth talks about the fractal of universes containing universes, which corresponds with the degrees of simulation, which I talked about before. And also there's biology. So in biology, there's Varela and Maturana who have this concept of autopoiesis as the cognition of living systems. And the idea of autopoiesis is that living systems are self-referential and self-regulatory, which is expression of the recursivity. And then we have Halberg in his concept of circadian rhythms. He coined the word circadian to reference the iterative, repeating nature of behaviors of organisms on a day-to-day basis. And then we have Lamarck and Darwin both discussing adaptation and evolution. And what is adaptation and evolution but iterations or recursions where a previous state of things meets the next iteration of propagation, and organisms that have certain characteristics that allow them to survive continue to propagate, and then organisms that don't have the characteristics for survival don't survive. And so we have this repeating iterative process that happens in organisms over both small periods of time and very, very long periods of time. And then we have Dawkins, who himself has even suspected that there may be a God gene, because how could there be this universal concept of God that persists across all the different nations of the world, and there not be something in us that is associated with creating the concept autonomously? And, well, from an architectonic standpoint, I propose that computation is that thing. It's the built-in simulacra of recursion that repeats a static, dynamic, and multidynamic series of orientations, which therefore iterates into all of the tessellations of our experience. And then we have neurology. So with neurology, we can start with Kurt Fischer and his concepts of dynamics of cycles of cognitive and brain development, and Werner's fractals in the nervous system. And then we also have Alexander and Globus's recursively organized neural systems. And then we also have expressions of computational simulacra that where people are giving expressions across a vast variety of physical sciences. We have Bertalanffy's systems theory, we have Poundstone's universal constructor in the recursive universe book, and then we have Mandelbrot, who coined the term fractal. And so these individuals present certain representations of phenomena that express these recursive characteristics in their attempt to nail down what's going on across all of these different systems. Philosophy. So there's three topics here: understanding, constructing ideas, and domains of experience. So Frederick Ferrier coined epistemology when that which naturally comes last has been made to come first, in terms of us understanding our understanding, which is clearly recursive. And then we have folks like Kierkegaard and Sartre, who discussed the idea of creating ourselves and creating our own meaning. So we recurse on ourselves to create our own understanding independent of necessarily the kinds of environments that we're in or the kinds of meanings around us that our societies share. And then there's Kuhn's Structure of Scientific Revolutions. And in that book, he talked about science being an iterative process. And then beyond that, we also have Weiner and his cybernetics and self-regulatory systems. And then we have constructing ideas. So we have Aristotle's syllogism, which is combining components together to make logical statements. And we have Kant's categories of quantity, which is unity, plurality, and totality, and then analytic and synthetic judgment. Unity, plurality, and totality are obviously associated with static, dynamic, and multidynamic, and analytic and synthetic have to do with the forward and backward directions of computation that I propose. And then Hegel's dialectics of thesis, antithesis, and synthesis, which is an upgrade or an updated version of Aristotle's syllogisms. And then we have Calivan's paraconsistency. And his idea is that if you have a way of knowing and doing that is reliable and produces useful results, then it is good enough, which is an answer to Kurt Gödel in some respects, which is to say that as you go through recursions, there are some things that continue to persistently work, and if they continue to persistently work, then you can continue using them because of that. And if there's a higher level of understanding or a higher level of integration, then you integrate those things when you can, but if you don't know it and what you're doing is working, then you can just use the way that you make sense of things, and that's good enough for that moment. And then there's domains of experience. And this has to do a lot with tessellations of computation. Plato had 3 parts of people: the nous, the psyche, and the soma, which is basically the body, the mind, and the spirit. And Descartes also talked about the mind-body separation. And Hegel had his objective spirit, subjective spirit, and absolute spirit. I would say absolute spirit is exactly synonymous with transjectivity, but it's definitely an attempt to express his characteristics. And then we have Peirce's Orders of Philosophy, which he inherited from Kant, which is the normative sciences, phenomenology, and metaphysics. And here it's dividing things into objective sciences, subjective sciences, and then transjective sciences. Or at least that's what metaphysics was originally attempting to articulate, is that these universal things that pervade across objectivity and subjectivity. And then we have concepts like materialism, panpsychism, and pantheism. And these are exaggerations of computational tessellation simulacra. Materialism philosophy exaggerates objectivity, panpsychism exaggerates subjectivity, and pantheism exaggerates the transjectivity. And in general cases, people who hold these positions think that their particular simulacra, in which they think is the foundational essence of everything, is the truth, and that the other points of view are completely wrong. But from an architectonic standpoint, I just mean to point out that there are philosophies that are entirely built on particular tessellates, and they build their entire worldview on them. Psychology and social science. So 4 topics: mind as a recursive system, absolutism versus relativism, transformations, and perspectives. So, mind is a recursive system. Hofstadter wrote a book called I Am a Strange Loop, and in this book he talks about how he believes that the human mind is a self-referential entity. Kurzweil also had a similar idea in his book How to Create a Mind, where he talks about the mind as a recursive fractal. And when we come to absolutism versus relativism, absolutism is the notion of things that are absolute, things that are universal, that are always true. And then we have the notion of relativism, which is that truth is relative to circumstance. And so people usually polarize between the two. People either believe that there are things that are absolutely true, or people believe that truth is relative. And people call these things by different names. So, for example, some people will reference absolutist thinking as the sort of like modernity or like pre-modernity, and relativism is like the postmodern way of thinking about knowledge. But the thing about this is that if you believe that everything is relative, then you're making a statement that relativism is absolutely true. And if you're making a statement about absolutism being always true, then you are taking into account all of the relativisms that allow it to be absolutely true across all the different relationships of a truth between things. And absolutism versus relativism sort of hopscotch over each other, or they sort of like leapfrog over each other. But in terms of like different ideas that people have about this in different areas of human experience, the different areas are things like ethics and morality, counsel and psychology across cultures, logic, understanding constructed knowledge, and processes used to devise knowledge. And this issue comes up again and again in all these different areas, and people argue about what's the right way to go about these sorts of things between absolutism versus relativism. And the absolutism versus relativism problem, actually, you can trace back to Gödel and his completeness and incompleteness theorems, where if you have one way that you make sense of things, there's always a larger scope that you haven't taken into account yet. So, in order for this to make more sense, we need to talk about transformations. So, the idea about transformations is that transformations are the changes that take place, or a sequence that happens in the recursive modes of computation. So, Jung talked about something he called the transcendental function, which is our brain's autonomous process of unifying opposites. And he demonstrated this was the fundamental symbolism that underpinned the alchemists in his book Mysterium Conjunctionis. Jean Piaget also had a take on this transformation sequence, and he named the different elements of the sequence: assimilation, accommodation, and equilibration. So assimilation is where people are confronted with new information that they relate to information that they already know. And accommodation is the behavior of people finding a way to relate the new information to that previous information that they have. And then equilibration is the synthesization process of combining all that information together into a new way of making sense of things. Kurt Fischer proposed a similar idea, continuing from Piaget's thinking, where he proposed that there are three different kinds of transformations that people go through with skills, where people first have singular skills, and then they have skill mappings where they relate the singular skills to each other, and then they have skill systems where the different relationships between the different skills that they have are combined into a system, which then serves as the basis for a new kind of singular skill. Michael Commons also followed along a similar lines as Piaget, where he proposed organizing components into combinations, and he terms these transitional steps between stages. And Commons' notion of this is that people first start with some sort of an equilibrium, and then new information is introduced, and this new information is either negated or it's complemented. And when people take this new information and they accept a certain new way of behavior in addition to their own, but they can't quite fit them together, then people take a relativistic standpoint and they'll oscillate between the different behaviors. So in some cases, they'll behave one way, and then in another case, they'll behave another way. And if people continue along this transitional trajectory, they eventually begin to try out different ways of combining the different behaviors together. And sometimes they'll overshoot and sometimes they'll undershoot. But if people manage to fit them together, then it creates a new kind of an equilibrium, which results in a higher stage of complexity of behavior. And Sarah Ross is worth mentioning here because she pointed out that Common's model of transition steps between stages is fractal. And it's fractal because the same transitional processes happen between every single stage of development of behavior. Now, we can look at the ideas that Piaget, Fisher, and Commons have here in terms of assimilation, singular skills, and the equilibrium all being associated with the static mode, and accommodation, skill mappings, and the relativism of commons being associated with the dynamic mode, and then equilibration, skill systems, and then what Commons called the smash transitions of trying to fit together behaviors into a more complex behavior as being expressions of multidynamic mode. So on the topic of perspectives, I'll just mention a couple things here. First, there's Carl Jung's notions of introversion and extroversion. There's a common misconception that introversion means that people are not social and they keep to themselves, and people who are extroverted are more open and social. But what Jung actually meant by these in psychological types, and he coined these two words, Jung meant that introversion is where people are more directed by their interior subjectivity, and extroversion is when people are more influenced by their objectivity of things around them. And Keegan continued along this lines of thinking where he combined it with his developmental psychology. And in his stages, he thinks that the transitions between stages goes something like this. You have some sort of internal subjective representation of phenomena, and then you attempt to create a reality around yourself based on that subjectivity. And when a person is able to create a new kind of objectivity that has been generated by their internal representation of things, then that objectivity becomes the new basis of their experience. And so people create new kinds of subjectivity in relation to that new kind of objectivity that exists. And then this goes on again and again as people go from one stage of behavior to another. And Ken Wilber's ACAL, all quadrants, all levels, is also worth mentioning here because he also deals with a similar concept in terms of the individual and collective over the internal and the external, which creates 4 different ways that people have perspectives about things. So the interior individual is subjectivity, the exterior individual is objectivity, the interior collective is intersubjectivity, and the exterior collective is interobjectivity. So you can see that the property of encapsulation is present here, where there's an encapsulation of subjectivity and objectivity, but then there's encapsulations within encapsulations with intersubjectivity and interobjectivity. Computer science. So here what I'm going to do is I'm going to talk about the universal computational simulacra of recursion, its modes of static, dynamic, and multidynamic, and the computational tessellations of objectivity, subjectivity, and transjectivity in regards to the characteristics that pervade all computer languages. And we begin with the Church-Turing thesis. And the Church-Turing thesis was that every calculable function is recursive.
And Curry carried this further with what he called the Y Combinator, and it was a mathematical expression of recursive functions being able to contain recursive functions, which themselves contain recursive functions, such that everything that they return can be returned to what was recursing them, and then that return can be returned to that which was recursing that ad infinitum. So what recursion really is in computer science is it's returning functions. And then by returning that function, it can return further functions, or it can return values that can be used for other functions. Now, static, dynamic, and multidynamic take expression in computer science as types, operators, and functions. So data types are things like Boolean, characters, integers, floating points, and strings, and people can create their own kinds of data types beyond that. And operators are that which operates upon the data types, which is assignment operators, arithmetic operators, bit operators, comparison operators, and logical and string operators. And then there are functions, and functions invoke data via parameters, and then they process that data via operations, and then it can return data. And so here we see that data types are the expression of static simulacra, and operators are expressions of dynamic simulacra, and functions are expressions of multidynamic simulacra.
On the topic of object, subject, and transject, I'm going to sort of glance over this because in order to give a full description that makes sense to you, the audience, about how these things relate to computer science, I'm going to have to talk about the ratiocinators that derive from them. And since I haven't went into detail about these things, and this is what is coming up in the next video, I'm going to put this to the side for the moment and then just talk about the properties of computational tessellation in relationship to computer science. So arrays are derivative of the properties of computational tessellation of an encapsulation of complexity. And so before I talked about different kinds of complexity, where there's horizontal complexity, where things are at the same rank, and then there's vertical complexity, which means that things are ranked, and then there's diagonal complexity, which means that things can return to a rank. So things can be jumbled up in different kinds of ways. And arrays are expressions in computer science of different kinds of complexity. You have an array or different variables or values that are all positioned in a sequence. And that sequence is always going to be horizontal complexity, it's going to be vertical complexity, or it's going to be diagonal complexity. We also see with incrementing the property of iteration of modes. So there's some sort of a static variable that represents a value, and then there's a repeating process of dynamic of operators that change that value again and again and again until it meets a certain kind of condition, and the resulting consequent of it is a new kind of multidynamism. It's a new state. And when we talk about public versus private, we're talking about different kinds of encapsulation. So there are some kinds of encapsulations that are public. So within a function, there can be data that is accessible to external functions. And when we're talking about private, we're talking about a kind of encapsulation where external functions do not have access to the internal data of a particular function. And then we have version control. And version control is the computational expression of the iteration of particular code that is written in a particular programming language. So as people go through different iterations of different simulations of code, then they have different versions and they keep track of them over time. And of course, that's an expression of the recursivity of iteration of different static states of the code going through different kinds of transitions. And then each transition results in a new state of the code, and then keeping track of that over time. Propositional calculus. Propositional calculus is about different ways that people represent how people assemble and disassemble representations or simulacra. And so here what I'm going to do is I'm going to put an emphasis on the connectives of different kinds of propositional calculi. And I'm going to do this by going through different eras, starting with the ancient world into the Age of Enlightenment, into the Industrial Era, and then into the Information Era. So Aristotle started with the notion of syllogisms. And syllogisms are where you have two or more premises and then somehow you combine them into a conclusion. And then your conclusion can serve as a new premise, which you relate to other premises, which you then combine into a new conclusion. So here we can see that there was already an earlier understanding of the recursivity of combining components into different combinations, combining different kinds of simulacra into more complex kinds of simulacra. Now, Chrysippus is the first person that I could find in history to talk very distinctly about connectives. And he used terms like if, and, or, because, and more and less. So the words if and because are associated with a particular ratiocinator process class. And so I'll get into that more in the next video on the ratiocinators. But for now, the words and or are associated with the dynamic mode, and the terms more and less are associated with the multidynamic mode. And in the Age of Enlightenment, we had Kant in his ideas of categories of quantity, which was discussed earlier in this video. And he talked about unity, plurality, and totality. And as I said before, unity is associated with static, plurality can be associated with dynamic, and totality can be associated with multidynamic. And his analytic and synthetic judgment classes can be associated, whereas the analytic is running the computation modes backwards, dividing things into parts, and the synthetic judgment is running the computation forward, combining things together into greater wholes. And Hegel had an updated version of Aristotle's syllogism in his dialectics with thesis, antithesis, and synthesis. And so we can associate thesis and antithesis to being different kinds of static, which are then associated together dynamically to create a multidynamic synthesis. Boole also dealt with connectives in terms of his absent, present, or an and. So something is or it's not, which are static representations. Either you're going to have a static entity that's present, or you're going to have a static entity that is not present. And then you had the connectives or and or, as we've discussed earlier, is associated with dynamic. It's the relativization. It's one thing or the other, the in-between before things are found to be an and, where it's not just A or B, but it's A and B together at the same time. And then Frege had his statement, negation, condition, and generality. So you have a statement, which is some sort of a static simulacra, and then you have negation, which again, like you are either accepting something or you're rejecting it through a dynamic simulacratic expression. And then you have a condition in which things can be combined as a multidynamic, and then this leads to a generality or a higher kind of static as the modes iterate and recurse back on themselves to create a new kind of equilibrium. In the industrial era, we have Pino, and he had the terms existence, intersection, and union. So again, we have static existence, and then we have the intersection, which is how things are related to each other dynamically, and then we have union, which is that multidynamic process of things combining together into a greater whole. And then we have Hilbert's introduction, elimination, conjunction, and disjunction. So introduction, you have a static element that is introduced, and then you have elimination, the negation aspect, which can only happen by relating things to each other through conjunction or disjunction. And conjunction is the forward direction of computation, and disjunction is the backwards direction of computation. Conjunction conjoins things together, and disjunction disjoints things into components. And then we have Carnap's provability, analysis, and synthesis. And with analysis and synthesis, again, we see this recurring theme where things are broken down into their parts or they're combined together into greater wholes. And then we have Gödel in his internally complete but externally inconsistent, and internally consistent but externally incomplete, as a proof of how this process works in mathematics. Zermelo-Franklin set theory has concepts of extensionality, specification, pairing, and union. So extensionality, you're extending the set of things that you account for as static elements, and you specify what these things are. You pair them with each other through dynamic relationships, and then you create unions between the pairings as a higher order representation, a new kind of a static. And then there was Church and his notion of types, operations, and recursions with his untyped and typed lambda calculus. And as we talked about before in computer science, types are associated with static, operations are associated with dynamic, and then the recursions repeat again and again. So you have types, operations, and then functions within functions within functions within functions. And then there's Tarski's truth functions, these connectives which are not, or, and, for all, and there exists. And so not is a negation. It's something not being true or not existing statically. And then you have words such as or, which correspond two things together, two or more things together dynamically. And then you have and, which brings things forward into relating two things together at the same time multinamically. And then there exists, which is that between these things that have been combined, you have something new that it comes into existence. And again, with the term for all, this is associated with a process ratiocinator, which I'll get into in the future video. And then we have Piaget with assimilation, accommodation, and equilibration, which I talked about previously. And assimilation is assimilating, it's bringing in new static representations or simulacra, and then having accommodation between the new simulacra and the previous simulacra that exists, and then combining them together into a new kind of representation as equilibration. And then in the information era, we have Chomsky's recursivity of grammar, which is that you have a word and then you combine that word with other words to make statements, but then you can compress those words down into a single word. And then you can relate that word to other words and then create another kind of a statement. And then you can create a word to compress all that statement down into just another single word. And this is a recursive thing that we can do again and again and again. And then, as I mentioned before, Fisher's singular skills, skill mappings, and skill systems, with singular skills representing static, skill mappings representing dynamic, and skill systems representing multidynamic. And then also, as previously discussed, there's Commons transition steps between stages. And so it starts with an equilibrium, and then something new gets introduced, and there's negation or complementation. And then when people take both or more things together and they can't quite fit them together, then they'll take a relativistic or an oscillatory position where they'll use a particular behavior in some cases and another kind of behavior in other cases. And then if people continue through the transition steps, they'll go through something Commons called the smash transitions, which is that people over or under exaggerate as they're trying to figure out a way to fit together different kinds of behaviors. And if they're successful, they create a new kind of equilibrium, which therefore becomes a new kind of a static. And so equilibrium is the static expression, the negation, complementation, and the relativism is the dynamic representation, and then the smash is the multidynamic representation or simulacra. And then we have Cook-Gruder, who I think is worth mentioning because she makes reference to a lot of different authors in developmental psychology and her concept of integration and disintegration. And of course, integration is the forward motion of computation, combining things together, and then the disintegration is the backwards motion of computation, dividing things into their components. So I think that I've driven the point here that there are universal characteristics of computation that pervade all of the different kinds of propositional calculi that people have across the eras and across many different meaning makings that people have in their attempts to try to nail down what's going on universally across human experience.
Part 3, discussion. So there are 4 sections here that I'm going to go through. The first is on computation in brain and mind. The second will be computation in social eras. The third will be succeeding from the meta. And then finally, computation in organism and machine. Computation in brain and mind. So 2 things, different brain regions resulting in different expressions of computation, and computation and personal growth. So first on different brain regions resulting in different expressions of computation. Computational simulacra is represented differently depending on the way that people use their brains to make sense of themselves and their environment. So some examples would be the parietal sulcus is required for mathematics, the temporal lobes are required for language, and the frontal cortex is required for logic. And of course, this list can continue, but the general idea that I'm trying to get at here is that computational simulacra is present within and beyond all of these. We use our brain functions to understand our brain functions. And by relating different orientations of experience to each other, we can separate out the computational simulacra from all of its variations. But we cannot express computational simulacra without employing brain functions to do it. And so what I'm getting at here is that in order to really grasp the concept of computational simulacra, we can only grasp it by relating ourselves to ourselves and feeling out the simulacra independent from all of the different variations of expression that it takes throughout our different biological and neurological systems. And maybe you can get a sense of where I'm going with this. We'll come back to this in a little bit. Computation and personal growth. As we have new experiences, our computational modal sequence forwards assembling and backwards disassembling simulacra, it happens via the means of computation, which are the ratiocinators. I'll be getting into this a lot more in the next video on the ratiocinators. But for now, this is just to say that the way that we experience things is based on the circumstances of our previous experience. And when computation stops running forwards to generate new simulacra between old and new experiences, we stop developing as people. Computation in social eras. So we can continue along the lines of this with computation and social growth. So just like how we as people go through these recursions over and over again as new information is being presented, cultures, institutions, and societies, and nations, they're identified by their unique instances of how they recurse collectively as groups. And developmentalism is the area of study concerned with identifying stages of development. Stages have sequences, like I've been previously discussing with figures such as Piaget, Fisher, and Commons. But each stage represents one recursion of the modes. And so this happens on both an individual level, and it also happens on a collective group level as well. And while the bulk of this sort of discussion is going to be reserved for the next video, for now I do want to talk about a couple of different kinds of developmental trajectories. So first we'll talk about academic development, and then we'll talk about socio-philosophical eras. In academic development, there are different kinds of disciplinarities that people have when they collect information together and they try to explain how things work. And so first we have just the standard disciplinarity, which is one specific field of study. And then we have interdisciplinarity, which is relating two or more disciplinary fields together. And then we have multidisciplinarity, which is relating multiple interdisciplinary fields together. And then we have transdisciplinary. And this is fields of study about all fields of study. And I have a bunch of references here, so if you're interested in seeing where I get this information or different definitions people also give to these terms, then there they are. But the trajectory also follows the computational modes. So disciplinary fields are static, and then interdisciplinarity is the dynamic of relating two or more disciplines together. And then the multidisciplinarity is the multidynamic of relating different kinds of interdisciplinary fields together all at the same time. And then when all of these are merged together as a higher level of complexity with a wide enough horizontal complexity scope, then we get transdisciplinarity, which is a higher order of organization, which is, like I said, the field of study about all fields of study. Now, in socio-philosophical eras, there's this trajectory of pre-modernism, modernism, postmodernism, and meta-modernism or transmodernism. Pre-modernism is usually characterized as being predominantly religious, where people have absolute truths that they believe have been given to them through some sort of divine revelation. And then we have modernism, which was the Age of Enlightenment, giving rise to the scientific method. And then we have postmodernism, and postmodernism is characterized by the relativity of knowledge. And then we have metamodernism or transmodernism, which is mediating between the modern and postmodern approaches. And I have a couple of references here from Turner and Frenrecht. But the thing here is that pre-modernism and modernism tend to have to do with absolutism, and postmodernism tends to do with relativism, and metamodernism or transmodernism has to do with combining these together. So we see there's the computational modes in the socio-philosophical eras of static, dynamic, and multidynamic. Succeeding from the meta. So I'm introducing three new terms: archdisciplinarity, arc theory, and arch-modernism. So archdisciplinarity. I propose that this is the field of study that studies transdisciplinary studies about all fields of study. And the architectonic of simulation gives us an orderly way in which to recursively relate the entire scope of all experiences to the entire scope of all experiences. And arc theory, I propose to be a theory about the arcs that persist through the recursivity of meta-theories and the theories that meta-theories theorize about. The previous section on the history of propositional calculus was an example of this. Most of them were meta-mathematics, meta-logic, meta-semantics, and meta-linguistics. And I demonstrated how the computational simulacra is the arc. It's the arc that they all share. And then the third term that I'm introducing here is arch-modernism. And I propose that this is an era of arch-disciplinarity and arch-theoretical social philosophy. And I don't think that this is going to happen in the immediate future, but this will be synonymous with the epistemological and the technological singularity. Computation in organism and machine. So 3 topics here: the recurring traits across simulators, simulated environments in organisms and machines, and then simulated intelligence in organisms and machines. So first on recurring traits across simulators. The only reason we've been able to create simulations in machines is by harnessing computational simulacra. And we harness computational simulacra on both the hardware and the software levels. It's the fundamental simulacra that underpins the computational machines. Computational machines have a different apparatic morphology than human beings do. We are biological, and computer machines are obviously mechanical, but the simulacra is still the same. Integrated circuits are the machine versions of biological neurons, and circuitry networks are machine versions of biological nervous system. And we can carry the same sort of analog between computational instruments with different biological instruments of human beings. So, on the topic of simulated environments in organisms and machines, since the apparatic morphology of machines is different than organisms, their simulations are produced by different apparatic means. So the way that it produces its internal simulations is going to be different than it is with people, but the computational simulacra is nonetheless exactly the same. And in terms of simulated intelligence in organisms and machines, artificial intelligence requires that the entity is able to reflect on itself and apply itself to itself. Like real artificial general intelligence is going to require this. And architectural and processual ratiocinator, which are the means in which computation computes, they haven't been clearly articulated in computer science. Like I said in the video on the architectonic of simulation, when I gave an overview about it, the thing is that you can't simulate an artificial general intelligence without a clear depiction of the architectural and processual ratiocinators that populate the range of the computational capacities of the entity that you're trying to replicate. If we want to have computer machines that are able to behave like people, we have to be able to account for the different means of computation in terms of their architectural and processual ratiocinators. And these have very specific sequences in terms of how each ratiocinator builds on a previous ratiocinator to create increasing levels of complexity. And so the framing problem, which is a common topic in the discussion of artificial intelligence, is only a problem because we haven't organized the ratiocinators in computer science. We haven't even included them in an organized fashion at all, which are required in order to define how intelligence works. So I'm going to continue on this topic in the discussion on the next video once I have went through the definitions and properties of the ratiocinators and how they have relationships to each other. And this brings us to the conclusion. So this was a pretty long video. It's the longest video that I've done so far. And the reason that I took so long to make the video and the reason that the video itself is so long is because I wanted to give a sufficient set of examples and be exhaustive about all the different associations that can be made to the universal computation of simulacra. And there are plenty more examples, and I'm sure that you, the audience, will be able to make a lot of connections that I didn't make in this video, or see further ways to continue along these lines of associations in general. And the next video is going to be on the ratiocinators, and then the video that follows from that will be on instantiation. So thank you very much for watching, and I'll see you in the next video.